Welcome to Malware Analysis with Python. I'm Professor Glass, and today we're going to be going over TrickBot Module Deobfuscation. As an overview, we're going to be looking at the strings of a module of TrickBot that was being injected into another process executable's memory space. This was captured using a debugger, and so that's where the binary from today's lesson is going to be. So from that binary data, we're going to be looking at strings. We're also going to be looking at hex dumps at a certain offset. We're going to use regular expressions to look for base64 encoded strings and base64 encoded character sets. And then we're going to decode potentially encoded base64 strings. And then we're going to classify TrickBot modules based on our observations from these strings. All right. So up front, I like to identify my samples, and this is something I do just every time. This hash is probably not all that useful because I pulled this out of a debugger, so you're probably not going to get this exact hash if you ran a sample of TrickBot. Just the nature of volatility of memory, but it's useful for me when I'm locally working with these samples. All right, so this is one of my favorite modules, is the hex dump module, and it basically gives us our 3-column representation of binary data. Traditional hex dumps, you've got your offset over here on the left, you've got your middle section here that contains the hexadecimal representation of each byte within the slice that you're looking at, and then on the right you've got your textual representation. So if there's any printable characters, ASCII characters, they get represented on the side there so you can read them. Here you're looking at the first 256 bytes of the file data object that we just read into memory, and just looking at a slice of the file data. And hex dump gives me the printout to screen that I'm looking for. I can tell just by looking at it that this is a Windows PE file. It's a process executable, but it doesn't contain your standard MZ header, and this is because this is something getting injected into memory and not necessarily a file you would find on disk. All right, so now we're going to use regular expressions to look for possible base64 strings. So base64 is an encoding standard that uses 64 characters to represent binary data. And it's those characters consist of uppers, lowers, numbers, and plus and slash. So here I'm using a regular expression to grab any string that contains uppers, lowers, numbers, plus, and slash that has a length of 10 or at least 10, but less than 500. We do see a lot of traditionally base64 encoded strings here. These look like they're representing text, but they're clearly not legible. This word executable is it matches our signature, but it's not a base64 encoded string. So we're going to have some false positives when you're casting this wide of a net. All right. So the next thing we're going to do is we're going to look at a hex dump from a string offset. So we found strings in the last slide, and now we're going to look at the index of that string within the data to see what byte offset does it start at. And it looks like it's 194,051 bytes from the beginning of the file. So what we're going to do is use a variable called offset and just throw that big number in there, and then we're going to hex dump file data using a slice that starts at the offset and then goes to the offset plus 256 bytes. All right, let's see. So finding custom base64 character sets. Base64 contains 64 characters of that are unique, and uppers, lowers, numbers, and plus slash. And what TrickBot does is, instead of using the standard base64 encoded character set, it uses a custom character set in a different order. So it's the same characters, just in a different configuration. So what we're going to do is use a regular expression to look for 64 characters in a row that fall within uppers, lowers, numbers, plus and slash, to accomplish, to see if there's any keys in that. And the way we determine if this is a valid base64 encoded character set is to sort them by byte order. So as we loop through these matches, we see we have two matches here. In the first one, when it's sorted, it prints out sequentially non-repeating characters. So you got your plus, your slash, you got your numbers, you got your uppers, you got your lowers. The second match that we have, because it was 64 characters, when it's sorted, it has a slash and a couple of zeros, a 2, 3, 5, 7, 7, 7. So you can see that it's not unique, it's not sequential. This is not a valid base64 encoded character set. All right, so let's make a function that proves this and sorts the good from the bad. This function here, find custom keys, basically does that, where it uses the same regular expression and then it compares it to this standard base64 encoded character set, and returns the keys that match that set when it's sorted. And then down here it will returns a list of the keys, and it used the set command to unique them, because sometimes there's duplicates. And it looks like the custom key for this module is this AKGU985E plus blah, 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 blah. It's cool. So now we found the custom character set used to encode those base64 encoded strings. All right, so now that we have the key, let's decode them. All right, so right here, I've got a function up top that just appends the padding for base64. All the strings need to be mod 4 or divisible by 4. So what this function does is it pads it with equal signs until the length of the string is divisible by 4. Then after that, we're going to loop through all the keys that we have. And then we're going to loop through all the strings that we have. And we're going to try to decode it. And we're going to do a quick sanity check here in the middle to see, hey, does the data that we decoded, are they all ASCII characters, or are they strings that I can read? If they are, cool, add them to my list. If not, then, keep on trucking. So let's move that. There we are. Decode UTF-8. Cool. Now, if we look at the decoded strings, we see some interesting stuff here. A lot of DLLs that are being listed here. Edge. Nothing really jumps out at me here. This looks like some sort of execution artifact, but I don't know it off the top of my head. I see Explorer, I see /C start, which may be something used with cmd.exe, but I'm not 100% sure on that. I do see this software, Microsoft Windows NT current version. There's a lot that goes on in this registry hive, so who knows. All right, so the next set of strings starts here, and some of the things jump out at me. I've got this WS reset, and that's a kind of a widely known UAC bypass. And coupling that with the HK current user, it looks like this particular module might be associated with UAC, but let's take a look. I have a slide for that. So for UAC bypass, during startup, the WS reset, which is used with the Windows Store to reset it on a Windows 10 machine, checks the registry value at HKCU software classes, appx 82 blah 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 blah, shell open command for a command to run. This binary will be executed with a high integrity as a higher integrity process without a UAC prompt for the user. So you can tell it to run a process with administrative credentials without a pop-up using this registry key. And there's a whole MITRE ATT&CK technique for it. And this is all based on the LOL project on GitHub. So shout out to those guys. All right. So now that we've figured out what this module is designed to do, let's write that down, or virtually write that down by making a list of signatures so that we don't have to know this information again. We can just scan it with this list of signatures. So what we're doing here is we're creating a Python dictionary, and we're using the for a key value pair, we're using the UAC bypass as kind of a key, and then we have a value here that contains that registry hive that's associated with the UAC bypass. So we loop through our signatures, and if the signature is in the decoded strings, then we can safely say that this module appears to be UAC bypass. So just a quick way to use the research you've done previously to as a force multiplier to know something quickly in the future. All right. So going to the next module. So TrickBot continued injecting modules. So this is the second one that I grabbed, and I did a MD5 on it just so I could identify which one gave me these results. And it looks like when I used find custom keys and it printed it out, it looks like I got 2 of them. And these, just spitballing them, look like they're both legit character sets. They passed the test. So we have 2 keys in this example. All right, so when I print the strings, again, we see executable because that's in the PE header, but then we see a bunch of stuff that kind of fits and kind of doesn't. So this module is a completely different module. So we are going to have different strings. So we'll decode and we'll see what we get. All right. So when I ran the function that decoded these, I used both keys and I used whatever strings that came up. And you can see that not all of those were successful. So you will have false positives when you cast this wide of a net. But we are doing a quick unstructured analysis of a binary, and we're not following the process execution of the code. So we're going to run into these sort of snags. All right, so we can see the snags start to clear up right around here, and we start to see some interesting URLs here. These look like URLs that are designed to return the user's external IP address, and check my IP at Amazon AWS, IP info. Icon has IP, myexternalip.com. So this feels like it's the part of the reason that these are in here is to get the user's external IP. All right, let's keep going. What else do we have? All right, looks like we've got caption, OS architecture, product type. So these appear to be things you would request from a WMI query. And again, this is just something that comes with experience, but these are things you can query WMI for. So, and it looks like it's used to like fingerprint the machine on a particular maybe botnet, or just get specific information about this particular endpoint. All right, it looks like it's got strings that are designed to show what it's going to report later. The host name, the OS name, the version, and these colons here, they don't serve like a programmatic function. It's more of just a pretty layout for whoever's going to be reading this. And you can see more of that down here. This Win32 operating system, Win32 processor, Win32 computer, those are WMI classes that you can query. And then we've got commands that are being run here. ipconfig/all get your network information. Netconfig workstation. These are very much like system administrative commands that are used to glean information about the endpoint that has been compromised. Very interesting stuff. All right, so let's add something that we found that was unique to the our list of signatures. So we're going to call this main bot, just as a we don't necessarily know what it is exactly, but it does cover a lot of ground, and we're going to just grab a particular string like ipconfig, and we're going to say that this is the main bot of TrickBot, and we're going to give it a label. And again, we're going to loop through our signatures, then we're going to loop through our through our decoded strings, and if it's there, we're going to print it out. And so now the next time we run into TrickBot and we decode the strings, we can then see, all right, quickly, this is the main bot, or this is the UAC bypass bot, or this is the whatever module that is being leveraged at the by the TrickBot at this time. So that is the lesson for today. That's it. So we covered strings, we covered hex dumps, we covered finding custom base64 sets, we covered decoding base64 strings, we covered classifying modules based on our observations, so that we can in the future work faster and know more about what we're looking at. That's all for today's lesson. Thanks for watching. I appreciate it.